So we're going to look at a phenomenon called diffraction. Now, when a wave passes through an opening, or it's next to an object, it kind of spreads out as it passes through the opening. You know this. You've experienced this with sound waves. You know, when someone's around a corner, you can talk and they can still hear you. The sound is bending around that corner. Now, light has a much smaller wavelength. In order for diffraction to occur, the wavelength needs to be on the same order of magnitude as the opening you're dealing with, and we'll say that's a distance. So, you know, you've got, so the simplest case, you've got like a wall and there's an opening in it. Right? In order for diffraction to occur, the wavelength needs to be on the same, well, not to occur, in order for it to be noticeable, the wavelength needs to be on the same order of magnitude as the width of this opening here, d. All right. So this also occurs with light, but since it has a much smaller wavelength, we don't see it, you know, bending around corners or anything like that because, you know, the width of a hallway is so big compared to the wavelength of visible light. We can, however, see diffraction with smaller openings. And actually, for purposes of diffraction, we're going to call this a W, a width, instead of a D. I don't know why, but that's what the book does. So we'll just follow that convention. Now, when light is incident on this slit, each point in the slit can be considered as a source of waves. Like, it's a source and then there's stuff radiating out in all directions. Now it's traveling to the right, so it's going to only really radiate to the right. But yeah, so we can consider each point as a source of waves. Right? Now, if we're going to make the same approximation we did when we were talking about two-slit interference, that waves hitting a particular point on the screen travel on essentially parallel paths. So again, we're making the assumption that, you know, the distance of this screen is much larger than the width of the slit. Right. Now, so obviously for theta equals 0, there's constructive interference. You know, if everything's going straight in, they're all going to be in phase. Huzzah! If we take two sources, so we take point 1 here, point 2 here, that are a distance, I need to make this bigger. So we take a point here and a point here that are a distance of half this width apart, then our path length difference then is this, which, just as it was for our double slit interference, this is just this distance, which in this case is W over 2 sine theta, is our path length difference there. And so, because, you know, it's W over 2 sine theta, we get destructive interference when W over 2 sine theta. These two waves will interfere destructively when W over 2 sine theta is equal to the wavelength over 2. Okay? And we can kind of walk our way down the slit and say that we could get destructive interference for these two and for two waves coming from here and here, and from here and here, here and here, and so on, all the way down. And so we can say that we get destructive interference when W over 2 sine theta equals the wavelength over 2, or when W sine theta is equal to the wavelength. And that's also going to happen for every multiple of that. If we just divide the slit into 4 pieces, then we've got a W over 4, and so we can say that W over 4 sine theta has to be equal to lambda over 2 for destructive interference, which means that W over 2, or W sine theta equals 2 lambda. And so we see that we have destructive interference where W sine theta is equal to m lambda, and m in this case is plus or minus 1, plus or minus 2, etc. Okay. And this is where we see the dark fringes on this interference pattern. Now, bright fringes aren't actually quite in such a regular pattern for diffraction. They are about halfway between the dark fringes, but they're not quite exactly in the distance between them changes as we go along, because as sine theta increases as wavelength increases, but this, for something times sine theta equaling a multiple of something, this angle isn't changing at regular intervals, because sine theta is not linear. So the bright fringes don't have quite the same consistent sort of pattern. It's not just where w sine theta equals 3 lambda over 2 or 5 lambda over 2 or whatever. It is going to be about in between those, but when sine theta is halfway in between two things is not when the angle is halfway in between. That's the point I'm trying to make. However, there is something to note, that if we take our prior relationship where we can use this and say that our first dark fringe is where sine theta equals lambda over w, and that's the first dark fringe above the middle. First dark fringe below the middle is where sine theta equals minus lambda over w. So if we consider the width of the central bright fringe, we can say that sine theta equals 2 lambda over w, and this angle. This is the width of the central bright fringe. Is where sine theta equals 2 lambda over w. For our L much bigger than w, we can use the small angle approximation that sine theta is about equal to theta, and therefore the angular width of the central bright fringe is about equal to 2 lambda over w. Right? And just as it did for our 2-slit experiment, the relationship that the height on the screen is equal to L tan theta also applies to this as well. Now, waves also diffract just when they go around objects. The book has a couple nice pictures. One is of the diffraction pattern formed by just a light shining on scissors. We typically think of objects as having, like there's light shining on them and they have this well-defined sort of shadow, but in reality, there are these little dark fringes that form around the object as well. Typically, you can't see this for regular objects, just with your eyes. The book says you can see this effect if you hold your fingers really close together. It claims that you can see bands of light and dark there. Maybe my eyes are just bad. I couldn't see it. Maybe, but you can try that and see if see if you can see that pattern. But it does occur for all objects. Like light bends through openings, it also bends around objects, and so the shadow of an object is not this well-defined sort of thing. It's really more like you've got your object and then the shadow. There is that darker area, but then around that shadow there's there's a small fringe of shadow, and then another small fringe of shadow, and then but it's a light area in between them. But these are so close together for these objects because the opening is huge. But they're so close together that you typically can't see them with your naked eye. But I thought that was kind of interesting.